Hello everyone, this is Miss Hanley here, and these are your notes number 6 to explain how to solve systems of equations using substitution. So you should already have a copy of these in your packet, so it's on the back of notes number 5, and the assignment for this is in your textbook. So just as you saw when you were solving systems by graphing equations of lines, you saw 3 different situations, 3 different types, right? So the first one was when there was one solution, and that was when your lines crossed, and they crossed in an actual spot. So that point that we see right here, that is your one solution system, when 2 lines intersect. So you want to think about the types of equations that would create 2 lines that intersect. It's not going to be 2 lines that are parallel, which would mean they'd have the same slope. They're not going to be the exact same line, but they're actually 2 different equations with 2 different slopes, and their y-intercepts could potentially be the same, but a lot of the times they will be different as well. When we talk about a system that has infinite solutions, that is a system where you have 2 equations that make the same line when you graph it. And we've looked at that a lot with the first few assignments. If there's a different version of an equation, just because it looks different doesn't mean it creates a different line. So you want to be careful when you get into some of these. You can once in a while notice right off the bat that the 2 equations would be the same line, but a lot of times you'll have to manipulate one to see that they are going to give you the same line. And then the last situation is when we have a no solution, so that's when you have 2 parallel lines here. So if it's a no solution, they're parallel, which means they have the same slope, and both actually no solutions and infinite solutions are going to have the same slope. The difference being here that with infinite solutions, it also has the same y-intercept, so it's the exact same equation. If it's no solution, where you have 2 parallel lines, then you have 2 different y-intercepts there. So that would be the difference between those 2 when you're trying to identify them. Alright, so let's do the first example that you have. It's a one solution system. We know it's going to be one solution. And when you're solving by substitution, you're trying to replace or substitute in a certain expression for a variable into the other equation. So you're taking one of the equations and putting it into the other. So one of the things that you want to look out for is you want one of your equations to be solved for a variable. So that is a key point here. We need one equation solved for a variable. And if you look at our 2 equations here, we have a y equals 3x minus 5. Well, this one that says y equals, that's solved for a variable. When you do substitution, it could be solved for y, it could be solved for x. It doesn't matter as long as it's solved for one variable. So as long as we know that y is equal to 3x minus 5, and we see another y in the second equation, we can go ahead and take what y is equal to and put it right in the place of y in the second equation. So we're sort of merging these 2 together. So once I've done this substitution here, my new equation would say 8x plus, and whenever I substitute in the expression, I always put it in parentheses just in case there's something I need to do with multiplication or anything. So we have 8x. The only thing I've changed is this right here, where it used to be a y. I now have a 3x minus 5. So if we look at the equation that we've just created, if there were a number in front of the parentheses here, then we would have to distribute. but there's nothing in front, so we don't really even need those parentheses. So we can go ahead and combine like terms, and if you look across this equation, I've gotten rid of the y value. There's only x's, and that's the way that you're going to be able to solve, because you can't solve an equation with both x and y. So if we combine like terms here, we're going to get 11x minus 5 is equal to negative 16. And then we want to solve this just as if we would solve any old equation. So if I'm solving for x, I need to add 5 to both sides, so that 11x is equal to negative 11, and then divide by 11. So x is equal to negative 1. And so if you think back to when you guys were solving systems by graphing, whenever you solved a system, you found an actual point where those two lines intersected. Well, we still need to find the full point, even though we're just working with equations. So we can't stop at just x equals. We have to carry this through and also find y, because every point has an x and a y. So you can take this value that you just found, x equals negative 1, and you can substitute it into either of your original equations. So pick whichever one you like best. And you always want to sort of pick the one that looks easiest. So I think the first one, y equals 3x minus 5, is easier. So I'm going to write this as y equals 3, but instead of an x there, I'm going to replace it with negative 1 minus 5. And then just simplify. So we have negative 3 minus 5, which would equal negative 8. So I found out that the point where these two lines intersect is going to be the point negative 1, negative 8. And we always want to write our answer as a point, as an ordered pair, because that's the actual solution to the system, not just one or the other. In the second block, we're going to solve a system that has infinitely many solutions. And we briefly talked about the fact that if you have infinitely many solutions, you're dealing with two equations that create the same line, so they should be the exact same equation. So when we're solving with substitution, remember that you want to make sure that one equation is solved for a variable, and that first one certainly is. It says y equals negative 3x plus 10. Then we can take this negative 3x plus 10 and substitute it into the y spot in our second equation. So let's write out what we'll have. We'll have, we will have 6x plus 2, and then instead of y, again with parentheses, we're going to substitute in what y is equal to. So negative 3x plus 10, that's equal to 20. I mentioned last time it was important to keep the parentheses, and that's so that I know to distribute here. So we're going to have 6x minus 6x, if I distribute, plus 20 equals 20. Well, 6x minus 6x, that is just 0. So what I'm really left with here is 20 is equal to 20. And a lot of people will be like, oh no, I did something wrong because all my variables are gone. But really, you did it correctly. You just have to look and say, is this a true statement? Does 20 actually equal 20? Well, yes, it does. So that would tell us we have infinite solutions here. You can also see that from the two equations that you're working with, right? If I took that second equation, 6x plus 2y is equal to 20, and I solved it for slope-intercept form, I would take away 6x and divide by 2, and so I end up with y equals negative 3x plus 10. Well, that happens to be the exact same equation that the first one is, that they gave us. So you can see the infinite solutions in multiple ways. The first way I showed you is with substitution, but you can also see it if you were a little savvy and noticed that those equations were really similar. All right, and so the last situation here is when you are going to get a no solution. So again, we have to make sure that one of our equations is solved for a variable. And in this problem, x plus y equals 4, 2x plus 2y equals 7. Neither of those say x equals or y equals. So we have to do that ourselves, and you want to think about which one is going to be the easiest. So if you have one in standard form and there's no coefficients, there's no number in front of the values, that one's going to be easy to solve for x or y. So let's take that first equation there, x plus y is equal to 4, and we're going to solve it for a variable. You could solve it for x or you could solve it for y. I'm going to solve it for x just because we've done all the other ones with y. So we would get x equals 4 minus y. Now that you have that, that's the equation, that's the piece that you're going to substitute into your second equation. But instead of putting it where y is, we're now going to place it where x is. So we would have 2, and then in parentheses 4 minus y plus 2y is equal to 7. Again, parentheses are important here so that we remember to distribute. So we have 8 minus 2y plus 2y is equal to 7. Well, if you look at that middle piece there, negative 2y and positive 2y, that's again going to give us 0. Those two things cancel out. So what I'm left with is 8 is equal to 7. Well, I know that 8 doesn't actually equal 7. That's a false statement. So when it's not a true statement, that's when you get a no solution situation. So there are no answers to this problem because these lines never intersect. You can also tell if you doubled that top equation like we'd been doing previously, you'd have 2x plus 2y is equal to 8. And the second equation was 2x plus 2y is equal to 7. So they're really, really similar, but because that last number is not the same, they're not going to give you the same line.